This video will cover the selection of a pump and mechanical sealing system for improving reliability. The design problem was posed by INEOS, a multinational chemical company. 3 deliverables are required for this project. INEOS requests the specifications of a new pumping system and a new mechanical sealing system. These deliverables will reduce downtime costs and hydrocarbon emissions. A life cycle cost analysis should accompany these specifications. Additionally, INEOS requests a program to estimate mechanical seal leakage. This deliverable will help them get a better idea of emissions.
There were 4 design solutions considered for the first deliverable. These included using a sealless pump with the current process conditions, such as a magnetic drive pump, using an updated centrifugal pump that is better suited for the current process conditions, altering the current process conditions and using a sealless pump, or using a reciprocating positive displacement pump. Various design methods, such as a qualitative evaluation matrix, were used to analyze the solutions. Factors such as cost, maintenance, and probability of process leakage were considered when making the decision. The final design solution chosen was a reciprocating positive displacement pump. A quote was obtained for a Milton Roy sandwich diaphragm pump. This specific pump meets all the process conditions, has no dynamic seals, includes an explosion-proof motor that is compatible with the plant standard VFD that INEOS uses, and it includes a pulsation dampener so as to protect the piping from the harmful vibrations that pumps such as a reciprocating PD pump can cause.
There were 3 design solutions considered for the second deliverable. These included redesigning the mechanical seal, applying API Plan 54, and applying API Plan 74. The Plan 54 uses a liquid as a pressurized barrier fluid, while Plan 74 uses an inert gas. Another matrix was used to evaluate these solutions. The final design solution chosen was API Plan 54. This plan uses an external lubricator system to pressurize mineral oil or ethylene glycol. This lubricator system contains a motor, pump, and a heat exchanging coil that uses water. It is similar to Plan 74, but ultimately proved to be more cost effective.
Deliverable is an Excel-based process loss system that quantifies the amount of fluid that escapes the pump via a faulty mechanical seal. The system models the behavior of a fluid mixture containing isobutane, propylene, and/or ethylene at a range of temperatures and pressures. This is the general process loss calculator setup. The colored cells here are locations for user input that define the type of fluid flowing as well as the pump dimensions. This area shows the equation derived in order to solve for the mass of the lost fluid. Some assumptions that are key to this equation being valid are laminar, linear, constant velocity and steady state flow of the fluid, and a constant flow area through the mechanical seal. The equation was derived using a selection of thermodynamic and fluid dynamic equations, and density and viscosity were derived using a process simulation program called PROMAX. After accepting each colored input, the program runs through scenarios in order to best select the proper density and viscosity from a property table. The calculator then calculates and displays the rate at which fluid is leaking to the atmosphere here.
Moving on to the lifecycle cost analysis, we can take a look at the difference between the new system cost and the existing system cost. On the left, you can see all of the values inputted for the system cost on the top in green for the new pump and lubricator, as well as on the bottom in blue for the existing Sunflow pump. For the chart on the right, you can see that the new system cost will be overall cheaper at about 6.5 to 7 years than the existing system.